Alright, so if you guys don't already know, I am Evan. I did take this class last year, so you guys can ask me for help. But probably within the next week or so, or else I'll be already begun. Alright. So, as you can see today, this is assignment 7 for you guys, right? In the book, it's 3.4, components of a vector and unit vectors. So this might make sense to most of you, and if not, well then...
Your voice volume's going to go up.
Okay.
Those people move forward.
Alright, I will speak... Oh, that's it.
Wow.
Yeah. The cone? Okay. Thank you, Kayla. Okay, so this is 3.4 in the book. This might make sense to most of you, and if it does, then great. If it doesn't, then this should be helped with an explanation. All right, so we're going to talk about components of a vector. So we're going to talk about what they are, how they work, and why they're good to use. So as you guys all know, vectors have two big characteristics, right? And they would be magnitude and direction. So when we were talking about, I believe you guys are already introduced to polar notation, right, of vectors. Am I correct? Okay. And direction. So you had r and theta as your, I guess, arguments or characteristics. And, you know, r is just the length, right? Length of your array or your vector, really your vector. And theta is the direction or the heading. So here's your length. And the length constitutes the magnitude of the vector. How big it is, how strong it is, whatever. And your theta is just your direction, your heading. You'll hear the word heading when you start to use navigation. Not like you're going to navigate anywhere. Just so you know. Not that I've navigated anywhere either, but just so you know. Okay, so that makes a little more sense. Now another way to describe a vector, not only with r and theta, but are to use the vector's components, or the book defines, or other books will define components of a vector as their projections along the x, y, and z axes. Now I don't know if that's significant to any of you. Maybe it is, maybe it's not. Regardless, we're going to explain exactly what that is. So if you want to write that down, you may. So a component of a vector sorry for my bad handwriting, is its projections along the, I went off the page, didn't I? The x, y, and z axes. Okay.
If you want to zoom out, press the zoom. Yeah, zoom out. It makes a little bit.
Should be good. Okay. Now, let's talk about what exactly that means. You guys have already added vectors. So let's say I'm adding vectors a and b to make another vector c, right? So here's my little xy plane. Here's my a, and here's my b. And those taken together, you get my c vector. And so that's fun and all. What you can do is, if I just wanted to describe to you vector a, it's obviously I want to describe its size and direction, but I don't want to use polar notation because maybe that's a little confusing. Maybe people aren't used to it. There's a reason why we don't use polar notation, and we'll figure that out shortly. Then I can do that with a if I just use its projections along the x axis here and the y axis here. So what I can do is I can just define vector a on its own as its x component, which I can label as, you know, vector a sub x, and then its y component, which I'll label a sub y. And just as I added a and b to get c, I can add a sub x and a sub y to just get, well, yeah, I can just get a. And so what you can do is you can take your quantity of a and x, a sub x. Wow, it's not a vector anymore. Oops. I'll just move it to the side. Well, you can take your a sub x value, put it next to your a sub y value, and that is just your vector a described in its coordinates of the x and y direction, right? So this is what we call the x component. And if you already can guess, this is the y component. So that's how they work. It's really not that hard, and the advantages using component notation will be revealed as you continue on in AP Physics. One big thing is when you start making dot products, makes things very, very easy. And when you start doing cross products as well, they make things a little more clear. Now, cross products are a lot harder than dot products, but don't worry about that for now. So the advantage, really, I wrote the advantage of using components to describe vectors are just, it makes things a lot easier and more quantitative. There's actual numbers to this, right? So I can put whatever number here. I can just say, oh, this vector A looks like it's 1, 3. And there you go. I've just described to you vector A in rectangular coordinates. All right. Now, this might also bring up the need to be able to switch back between polar and rectangular coordinates, right? So if I give you a vector, let's say I throw a ball, let's see, 10 meters per second at like a 33-degree angle, and you want to write that vector in rectangular coordinates, well, you got to figure that out. Okay, so let's go ahead and do that. So again, you're starting with your xy plane. You got that vector, has that length or magnitude r, has that direction theta over there. And so what we want to do again is to turn this into its components. So without even calculating anything, we can already see, okay, well, and let's call this vector b. That one vector right here. So we can already see, okay, I can see that the component of b along the x-axis, or its projection along the x-axis, is just right here. Right? And then along the y-axis, it's just right here. And for those of you, which you should have already taken it, taken AMA or trig, this is just an easy cosine sine identity problem, right? So if we figure out what's the cosine of theta, well, if you remember SOHCAHTOA, you guys remember that trick? Nice trick, right? SOH, is it SOHCAH? Yep, CAH, and TOA, right? So we're using cosine here. So cosine equals the adjacent over the hypotenuse leg. So here's our adjacent leg down here. So if we take this adjacent leg, or b sub x, and we put it over the hypotenuse, then we have our equality. That length is r, or you can say b, right? The full length of the vector is b. For sine, it's going to be opposite of our hypotenuse. So we have b sub y over b. Okay? And now remember, our whole goal here was to find what our components were. And so all we have to do is multiplying cosine both sides of this equation by b, both sides of this equation by b. And now we have b, or the magnitude of the vector, multiplied by the cosine of the direction, or the theta, gets you the component of the vector in this case, the x direction. Now I say in this case, and in most cases, a cosine will coincide with the x direction, but it really depends on what where you're referencing your angle from. Okay, so we'll talk about that a little more. Hopefully, we'll have some time. But if you're referencing your angle off the z-axis or the y-axis or some imaginary axis, I don't know what you're doing, right? But if you find cosine through that, that's the axis you're measuring from. Okay. And also, b times sine theta will get you the component of the vector b in the y direction. So that's pretty nice. And of course, you can use this same idea to go reverse, right? If, let's say, you didn't know how fast I threw the ball, or in what direction I threw the ball, but for some reason you know the components of the vector at which I threw the ball. Well, then you can figure out using the Pythagorean theorem how fast I threw the ball, and then use tangent to figure out at what direction I threw the ball. Right? So Pythagorean theorem, c squared equals a squared plus b squared, where c is your hypotenuse and a and b are your legs. So in this case, your legs of the triangle are the b sub x and the b sub y. Your hypotenuse is just b, the value b. And so we can say b squared equals the x component squared plus the y component squared. And so you know these, right? In this case, you know these two values. And off from that, you can determine the magnitude of the b vector. Again, you know b, x, and y. And if we remember that, I'll move this up. If we remember that tangent of theta equals your opposite over your adjacent, we can say, oh, tangent theta just equals b sub y over b sub x. And then use inverse tangent to say, oh, now I know the angle at which I launched the ball. Any questions so far? Or is this crystal clear, making perfect sense? Because it doesn't have to. Eventually it should, but okay, no questions. All right. So once we got all that down, and that's like, oh yeah, that makes total sense. Thanks, Evan. Okay, there's more. Don't worry. So now we're going to talk about something that's equally as easy, equally as important, but sometimes is also confusing the first time you learn it. Mainly because it's just like, it seems very arbitrary. And I believe it is, right, Mr. Lake, the whole I had? Jake?
Yeah, I had to pick 3 letters.
Yeah, so it's kind of arbitrary, but there's a reason to it, and we'll talk about that. So we're going to talk about unit vectors now. And for those of you that are taking Math 6 or have done something similar to multivariable calculus, you will have had introduction to what, I hat, which is like this, j hat, and k hat are. And they're really cool, but there's more of a use to them. But let's define what a unit vector is. And a unit vector is a dimensionless quantity that has or having a magnitude of exactly 1. And denotes only direction. So really that is essentially the use of the unit vector. The unit vectors of I hat, j hat, k hat, and any unit vector ever. Okay? All they do is note direction. Manuel, you have a question there.
I was wondering how it was dimensionless if I was about to ask.
All right. I was actually thinking about that same thing yesterday, and I figured it out, because what you do is you invariably will start using these unit vectors to describe displacement or speed or acceleration, right? And so the problem is, so for example, let me just jump ahead so you see what I'm saying. I can say like, okay, v naught, or the initial velocity, which is a vector, equals 2 in the I hat plus 3 in the j hat minus 7 in the k hat, and then I do this and I say meters per second. Okay? The problem is, if I has a dimension, dimensions include seconds, meters, kilograms, pounds, but that's not SI, so I don't use pounds. But if I had a dimension, then all of a sudden your velocity component has the wrong amount of, has improper dimensions, right? Your velocity vector needs to have some kind of unit of length over some kind of unit of time, whether that's feet per minute, miles per hour, kilometers per, I don't know, year. Yeah, Kaylin?
When you actually say dimensionless, you're not saying that I, J, and K are dimensionless, because I assume that I, J, and K already have predefined dimensions on them, like X, Y, and Z.
Okay, can I butt
Please.
in here a little bit? What do we mean by dimension? We mean units of time, length, or mass, temperature, some combination of units, right? I hat, j hat, and k hat are basically a way of saying, hey, this stuff is in this direction. Now, if I say a direction, does a direction have any units? If I say to the west, does that have any units of time? No. Length? No. Temperature? No. Mass? No. It has no. It just means to the west. It's just a way of saying a direction, and a direction doesn't have any units. But the stuff that is in that direction might have units. Like in his example up there, velocity, meters per second. It has units. So if you say you're going 2 meters per second to the west, well, what units does that have? It has units of meters per second. To the west changes nothing about that. It just says what direction it's in. Okay, so it's not, so therefore, the I hat means to the right or whatever, along the x-axis. That's dimensionless. It doesn't have any units associated with it. Does that make sense? You look skeptical.
Well, no, I guess yeah, it sort of does make sense.
It does have meaning. Dimensionless doesn't mean it's meaningless. It just means it doesn't have any of the units of quantities that we meant associated with it.
Because just from what I've got so far, I've always thought that I, J, and K were they were their own separate vectors already. I didn't know that they just denoted direction. I thought they were already their own separate vectors. I would be 1, 0, or 1, 0, 0. That is the vector, and it already has the.
But what units does it have?
It's the one that is.
But that's just a quantity. That's just a magnitude.
But what units does it have? Meters? Meters per second? Acceleration?
Picoliter?
Yeah. Okay. That's what we mean by dimensions. That's something that always throws people off.
Yeah, really. Hold up, you guys. Listen up. Really, whenever you hear unit vector, direction is all you need to think. All you need to think is direction, and all you need to know is magnitude equals 1. So it doesn't change how big or how small or how whatever the vector is. Okay? And so, just going off this example, okay, what am I saying here? That velocity is 2 in the I direction, 3 in the J, -7 in the K meters per second. What am I saying? I'm saying that, let's say this is a particle, all right? Let's say this is like, a speck of dust. I don't know, electron. I don't know. Whatever it is, it's got this, it's got this V naught thing going on here. Okay, so here's my x directions down here, and so this is my component of velocity in the x direction or the I hat direction. Okay, so what you have to realize is when you hear, see, whatever, think of I hat, it just describes direction, or I'm gonna say it just describes direction, I would say along the x-axis, but let me also say that it's positive direction. So it describes, okay, I'll write it better in the other two. This is positive. So if it was going, back, I know this is like broken English right here, But if it was going backward, right? If you're going from, 5 to 3 to 2 to 1, it's still I hat. It's just negative I hat. You see? Okay. So I hat describes direction along the x-axis positive, and j hat will describe, this is how I should say it, describe, does this make more sense? Positive direction. Help me out here, guys. Come on. How do I make this make sense?
Can you draw a three-dimensional graph, since we've mostly been working with 2 dimensions as of yet?
So you want me to draw 3 dimensions or no?
Well, I understand, but
3D, right?
Well, you're going to get to that on the computer thing.
Yeah, a little bit.
Okay, j hat means in the positive y direction.
That's just wait no. That
I is your x, j is your y, and
Okay.
k is your z.
The natives are getting restless.
Yep.
I think you can just say vice versa.
Okay, again, arbitrary. These letters these could have been like lambda, nu, and phi or something, and everyone would have been happy with it. Okay? Because in fact, later, once you get to E and M, that's the second semester, Evan. Who cares? You should. You're gonna start using like r hat and like theta hat, and theta hat comes out from the center. Blah 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 blah. Oh no, r hat comes out from the center. Theta hat is like a unit of radian. I don't know what it is. We never used. We just talked about theta hat. We never actually used it, but you will use r hat. But again, it's just arbitrary. We just say that the unit vector I talks about direction in the positive x direction. I just use direction talk. And we just say that the unit vector j describes positive y direction and k positive z. That's it. That's all you need to know. It doesn't change anything. Just like what Mr. Lick was saying, it's just if I tell you, Gage, I'm in a car. I'm not driving it because I don't have a license yet, right? But I'm in a car and it's going 40 miles per hour, okay? And then I tell you, I'm going 40 miles per hour northeast. That's it. That's all the J, K, and I do. I, J, K, that's all they do. They're just saying, I'm going 3 meters per second in the Y direction. I'm going 7 meters per second in the negative Z direction. So you're going underground. I don't know. But you see what I'm saying? That's all they do.
I know what you're saying.
I'm just saying.
Does everyone else know what I'm saying? Yay! Okay. Well,
I know.
okay.
He likes to throw wrenches.
Of course. Yes, of course.
Electric wrenches. Because those are very powerful crap.
This particle. Okay. All right. So let's go ahead and talk about our vectors A and B from over here. Right. So for vector B, let's just say B had magnitudes of 4 and 4. in the x and y directions, or the components x and y. So how do we write that? How do we write A is 1, 3 and B is 4, 4 using these I, J, K vector hats unit things? Okay, easy. All right, so let's go take a look at this. We have vector A, which we said had the components of 1 and 3, and vector B, which we said had the components 4 and 4. Ooh, I should stay consistent. Okay. All you got to do is say, hey, you know what? Vector A has got 1 unit of x direction to it, and it's got 3 units of y direction to it. Okay? So you can say that vector A is going 1 unit in the I hat direction, and also positive 3 units in the j hat direction. And for vector B, we're going 4 in the I, and 4 in the j. And might as well be. I was explaining 3D. Might as well throw in an example. If it was negative 1, positive 1, and negative 4, I would just write my C vector using the I, J, K hat unit vectors as, I can just say negative I plus J minus 4 K hat. And so right now, again, to be clear, they have no direction. They have no, they have no dimension. And then I can add dimensions onto this vector as I see fit. Okay? So, let's see if I can be a little fancy and use my computer here. Okay. So let's go ahead and add these vectors. So if I want to say A hat, vector A plus vector B, and we'll do vector C as well. So we'll make a new vector D. It's just like, it's just simple addition, but all you got to do is multiply each component together. Add, my bad. Add corresponding components together. So for A, I would say, okay, I got I hat plus 3j. For B, you got 4i plus 4j. And then for C, you got, negative I plus j minus 4 k hat. So you're adding all these up. So let's go down the line just like you usually do. So again, it's implied that you have a 0 k hat here. 0 plus 0 minus 4 is negative 4. So 3 plus 4 plus 1, right, is 8. And 1 plus 4 minus 1 is just 4 I hat. And so we can describe the D vector as such.